Hello and welcome to another graduate classical mechanics video from Dr. Webb. Today we shall be studying a rather interesting example, and that is the deflection of a particle that is dropped from a certain height. Now, why should it get deflected? Because the Earth is rotating. So because you are stuck on the rotating Earth, you think that the particle has deflected, whereas all that's really happened is that the particle has fallen down like it always does, and the Earth has rotated from under it. We're going to do this using two-way methods. One is the equations for a non-inertial reference frame, which I shall first derive, and then we'll use the procedure outlined by Coriolis. And meanwhile, Newton had his theory of gravitation, and that led to different kinds of orbits. The particle that's dropped from a certain height is just an example of a specific trapped orbit. So we can use the theory of orbits to see what that would predict. And we shall try to compare the two methods. So first, let's derive the equations for non-inertial reference frames. So let me draw two reference frames. The frame indicated with a prime means that it's a fixed inertial reference frame. So that is the frame in which I am located. And then I observe another frame, which I'll call S, that is somewhere else. So this frame could both be translating and rotating. So there's a translation vector, capital R, that relates to two origins. And then the unit vectors in this frame will be called E1, E2, and E3. Now, for convenience and simplicity, we'll assume these frames are both orthonormal reference frames. In fact, we will use orthonormality in a essential way to drive the equations. So first of all, the orthonormal triple is E1, E2, and E3 in the frame we've called S. And S is the frame which is non-inertial. So S prime is inertial, and S is non-inertial, which means that it's both moving and rotating. Now, what we are trying to do is trace the fate of any vector. So a vector in the frame S prime, how will it be described in the frame S? Now, all vectors can be moved parallel to themselves, so I can move the vector parallel to itself and situate it at the origin of the frame S. Then we have the following equation for the rate of change of A. A dot is the rate of change of the first component times E1 plus the rate of change of the second component times E2 plus the rate of change of the third component times E3. This is how the person in S would determine the rate of change of a vector. In the person fixed to S will not see E1, E2, and E3 as changing, but the person fixed to S prime will see those things as changing also. So if this vector is fixed in S prime, this person will not see the components of this vector changing. That person will see the components of the vector changing. That's why you put a dot on the A1, A2, and A3. This person will see the components the same, but he will see the E1, E2, and E3 changing. So in S prime, the story is going to be like this. A dot prime, which is the vector as described in the prime coordinates, and that's going to be whatever you had here plus an additional change coming from the fact that E1, E2, and E3 themselves are moving. So these A1 dot, A2 dot, and A3 dot come from whatever is going on with the vector A. Maybe it's expanding in all three directions, or expanding in two directions and contracting in one direction. That vector is free to do whatever it wants to do. So that is the absolute nature of the vector A, as seen in the frame S. But in the frame S prime, there's that absolute change plus the relative change coming from the fact that E1, E2, and E3 themselves are changing. So now it's a question of comparing these two descriptions of the same vector. Now, the same vector has to be described in two different ways. So now what we're going to do is we're going to make an assumption about the transformation that relates S and S prime. We're going to assume the transformation is a linear transformation. So that's a pretty big assumption. Linear transformation means that EI dot will be some zeta ij times ej. This tells you the rate of change of a unit vector is proportional to some other unit vector. So this is the assumption of linear transformation. And here I've used the Einstein summation notation, which is that repeated indices are summed over. In this case, the index j is summed over from 1 to 3. And for the purposes of this exercise, we're going to assume that all these zetas are real numbers. Right now, it seems that there are 9 zetas. In fact, let's write them all out. It's a good exercise to see what this really means. Einstein summation saves us so much space because in reality, this stands for the following system of equations. When you put I equals 1, I'm going to get zeta 1j ej. That means it's zeta 1 e1 plus zeta 1 e2 plus zeta 1 e3, and then e2 dot. Now I is equal to 2, but j is going to be 1, 2, and 3. So that's zeta 2, 1. And lastly, E3 dot is zeta 3, 1, E1 plus zeta 3, 2, E2 plus zeta 3, 3, E3. So it seems at first blush that there are 9 undetermined components of zeta, but we have not used the orthonormality. So let us impose the orthonormality condition. If these 3 unit vectors are orthonormal, then the orthonormality must be satisfied even with respect to the derivatives. So that's the next thing we'll do. EI dot EJ equals delta IJ. That's the equation that orthonormality buys us. And here delta IJ is Kronecker delta. It's equal to 1 if I is equal to J and 0 otherwise. So I'm going to differentiate this with respect to time. Because time is an important element in all this. So let's do that. Well, when I differentiate with respect to time, I'm going to get, by the Leibniz rule, 2 terms. Let's write those terms. I'll get E1, EI dotted with EJ, EI dot dotted with EJ, plus EI dotted with EJ dot. And that's equal to 0. Now let's substitute for EI dots from this assumption of linearity. So I get zeta ik ek instead of EI dot, and that's dotted with EJ dot, just EJ. And then here I have EI dotted with EJ dot, which is going to be zeta jk ek. So I'm very careful that the summation indices are not the index that appears over there, because I and j are both free. All right, now ek dot ej is just delta kj. So I'm going to get zeta ik times delta kj. And here the zeta jk are just numbers, so they come up front. And then I have ei dot ek, which is just delta ik. And that tells us something important. This is only non-vanishing when k is equal to j, so I get delta ij. And likewise, when I is equal to k here, so that means I get delta ji equals 0. Delta ij plus delta ji is 0. This tells me an important equation that if I is equal to j, then delta ii equal to 0. So the matrix is traceless or trace-free. This additionally tells me that the matrix is antisymmetric. So, and this particular thing tells me it's trace-free, as well as for each value of I, it's 0. So it's trace-free as well as 0 elements along the diagonal. All right, so now let's write down this equation. Actually, let me write it out in full form just to show you how it would look in a matrix notation. So in matrix notation, I would have E1, E2, E3, the whole thing dotted, is equal to, then I have zeta 1, 2, zeta 1, 3. And then here, instead of zeta 2, 1, I'm going to have negative zeta 1, 2 from the antisymmetry property, 0, zeta 2, 3, and then negative zeta 1, 3, negative zeta 2, 3, 0, applied to E1, E2, E3. So those who are sophisticated or advanced students already know what this is. It's a Lie algebra of the rotation group. But we don't need to know it. That's the point. We can stumble along and discover it as though by exploration, like I have done. So now we can write this equation that I've written there. What will the equation A times E1 dot A1 times E1 dot plus A2 times E2 dot plus A3 times E3 dot. I would like to express this now in terms of our new notation. Well, this dot product is actually a matrix multiplication. It's a multiplication of a row vector, A1, A2, A3, like that, and the column vector, E1, E2, E3, with the whole thing dotted. So now I can apply this to the right-hand side. So I'm going to get this to be A1, A2, A3, and then I have 0, zeta 1, 2, zeta 1, 3, negative zeta 1, 2, 0, zeta 2, 3. So I complete that, and then I write this as E1, E2, E3. So we are discovering the rotation matrix. So when I multiply these, let me do the multiplication here first. A1 will get nothing, A2 will get negative zeta 1, 2, A3 will get negative zeta 1, 3. Okay, so we'll do that. I'll do it silently so I can think as I'm writing it. I'm going to create barriers so we may keep track of all the elements. Here I don't get any term with A2, but I get A3 with that. A3 will make no contributions because of the 0 here. And then this goes along for the right. All right, now this looks like a, we're going to get an interesting result, and it will turn out to be what we are after. Now, because this is a number, eventually it's going to be a single number. That number can actually be written as the following determinant. Now you can see determinant-like structures appearing already. So those who know determinants would have seen this coming. So this can be written after multiplying through. I can write this as E1, E2, E3, zeta 23, negative, zeta 13, zeta 12, A1, A2, A3. So that's the upshot of doing this. So what we can do now is invent, using our antisymmetric circle symbol, also known as the magic circle, we can invent components of angular velocity. So I'm going to call zeta 23 the angular velocity omega 1, zeta 13 negative omega 2, and zeta 12 omega 3. So we have discovered that the rotation rate is given by this angular velocity component. So the upshot is this vector A1 E1 dot plus A2 E2 dot plus A3 E3 dot is just given by the determinant but the determinant is a cross product. So this is just omega cross A. In this manner, we have this very important insight. This is actually a theorem known as Euler's theorem. What we have proved is known as Euler's theorem. And Euler's theorem says there exists a unique angular velocity omega that generates the infinitesimal rotation. So unique generators of infinitesimal rotation. It's basically the Lie algebra of the rotation group O3. So those who are interested in group theory can look it up. My intention is to use this to do some physics, so we'll keep that as our aim. This tells us that the rate of change of rotation as seen by the person in the inertial frame is equal to the regular rate of change of rotation plus this, which is given by omega cross A. This can be, the vector A is completely incidental. We don't really need it. So we can remove the vector A. How do we do that? We can write d by dt of anything in the frame S prime is equal to d by dt of anything in the frame S plus omega cross. So this is the symbolic equation that gives you the transformation from inertial to non-inertial frames. So I'm now going to have to derive the equations. This is the operator, operational equivalent. So I'll call this the operator. And we're going to apply this operator to find out the new second law of Newton. So we're almost there. Let's take some examples. Now that we have gotten this far, it might be a good idea to have some examples of this operator. So one example is, suppose you have omega itself. What does it look like? How does omega transform? So if I have d by dt omega in the frame S prime, that's going to be d omega by dt in the frame S plus omega cross omega. Well, omega cross omega is 0 because a vector crossed with itself is 0. This tells us that angular accelerations are absolute. This is, if you like, the proof of the famous thought experiment that Newton had with Bishop Berkeley, known as the rotating pail experiment. You can look this up. The rotating pail thought experiment was an important experiment in the history of philosophy, of science, because it proved the existence of what's called an absolute reference frame. Newton set a pail rotating in his imagination, or maybe he did really, I don't know. And the concave shape, the paraboloid shape of the water, he attributed to the inertial attraction of distant stars. So that's the proof that angular accelerations are absolute is right here. Now let's do the Newton's second law using this operator. Newton's second law is F equals ma. So we have to find the acceleration vector r double dot in the prime frame. Well, that's going to be r dot in the prime frame, and then another dot also in the prime frame. So each of these dots refers to that operator. So let's do that operator. So I get d by dt in the prime frame. What is r dot? Well, it's going to be r dot plus r dot, because don't forget that these two vectors are displaced by a vector capital R. That also can change. So, and then of course we have this omega cross R. Now because this d by dt prime operator is got d by dt plus omega cross, we will do that again. So this is d by dt plus omega cross of everything here. So let's proceed. What we're doing here is r double dot prime. I take the d by dt inside. So I get, I'll do this term first for the d by dt inside. So I get r double dot plus r double dot. And then when I take the d by dt to the omega cross r, I'll get two terms. And the first term is going to be omega dot cross r. And the second term is going to be omega cross r dot. So I finished d by dt. Now I do omega cross of all this. Well, that's going to be omega cross r dot plus omega cross capital R dot plus omega cross R. All right, that is quite complicated, as you can see, but there are some terms in common. For example, you have omega cross R dot here and omega cross R dot here. So you have two of those. So let's do a little bit of term gathering. Nothing can be done about that, so we'll just keep that omega dot cross R. And then we have omega cross capital R dot, and then omega cross R. So I've gotten down from 6 terms to 5 terms because I've combined two of the terms with a factor of 2. So that's about the only thing I've done. Now, this is a very complicated equation, and you really don't probably need all these terms. However, there are some names, and let's get familiar with the names of some of these terms. The Coriolis acceleration, A cor, is that term with the 2 factor except with a negative sign. And then there is a quantity called the centrifugal acceleration, which I'll call ACF, and that's negative of this term. Now, centrifugal has got a bad rap in elementary physics because we're never supposed to use centrifugal, it's only centripetal. But since we are going to be in non-inertial frames, we're going to feel the flinging out effect in a non-inertial frame. So the centrifugal is appropriate. If you're freaking out, then I'll tell you what the centripetal is. Centripetal acceleration, which I'll call ACP, and I'll never use, is just negative of ACF. All right. So we have our famous equation. The sum of all the external forces is equal to mass times acceleration, which is called Newton's second law. So let's write it. Sum of all the external forces, Fx, is equal to mass times the acceleration, r double dot, in the prime frame. Well, now we can substitute all these terms. So I'm going to get, it's going to be m r double dot plus m capital R double dot. And here, I'm going to write it as negative F Coriolis, where F Coriolis is mass times A Coriolis. And then I have plus m omega dot cross r, and then that term. And then here, I'll write that as negative A centrifugal times mass, which is negative F centrifugal. So let's count the terms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Should not have 6 terms. Let's see. I think I may have missed a term here. So I'm supposed to have, I think, more than one term. So that's 1, 2, 3, 4, 5, 6, 7. 7 becomes 6. So 2 of these combine, omega dot cross r, omega cross r dot. So I must have missed a term. No, there are 6 terms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I was just confusing myself. There are 7 terms there and 6 terms here. All right, this is beautiful because now we can write mr double dot, because mr double dot is what we are interested in the frame S double prime. Mr double dot is going to be the sum of all the external forces. And then you'll see 2 additional forces. If I transfer this over to the other side, you're going to see a Coriolis force. So in your frame, you're going to experience a deflecting force called the Coriolis force. And then you're going to experience also a centrifugal force. You're going to be flung out in the rotating frame. And then you have a few other terms, which I'll also write, mr double dot minus m omega dot cross r minus m omega cross r dot. In most applications, these terms will drop out. So we'll just have these three terms. So this is our equations. We have done the first part of the problem, and that is found the equations. So the specific application we have in mind is that of the Earth. So the reference frame with respect to the distant stars and the reference frame fixed with respect to the Earth, let's suppose they both have the same coincident origin. So r double dot is 0, and the rate of change of the Earth's rotation is very negligible. Earth is really not slowing down or speeding up. And so all of these terms will just go to 0. So I'll just have these three terms. That's going to be our next important application of this equation. So in our agenda, it's item number 2. Apply it to find a Coriolis deflection of a drop particle. That's the thing we're doing next. So Coriolis's computation begins with drawing a picture of the Earth. Let's do that. All right, the place we are going to be stuck on the Earth, I'm in Rochester, New York, so that's around, the latitude is over there. So that's going to be my reference frame because I'm stuck to the Earth at that point. So my reference frame will have my x-axis like that, my z-axis, and my y-axis will be perpendicular to the x and the z-axis. Because x cross y is equal to z, the y-axis will be into the page. So that's going to be my y-axis. All right, the angle lambda is called the co-latitude. Sorry, it's called the latitude. The angle theta is called the co-latitude. So we're going to drop a particle from a certain height above the ground. And initially, it's going to be dropped with 0 speed, and it's going to keep speeding up as it comes towards the Earth, converting its potential to kinetic energy. But as the speed develops, you're going to get these Coriolis terms, because as you have r dot, which is the radial speed, you're going to get omega cross r dot, and that'll cause the particle to be deflected either east or west. Okay, so we'll talk about that deflection very soon. Now in my coordinate system, if that's my omega, I can transfer that omega over here, and I realize that this angle is theta, and this angle is lambda. So those are my angles over there. So we're going to make a few assumptions. The first assumption is that the height is much less than the radius of the Earth. So what that buys us is that the acceleration due to gravity is constant. So if the height is a couple miles, for example, that's a pretty good assumption. If you're going to drop it where the moon is located, then of course it's not a good assumption at all. Now we're going to also assume that as it comes down, you're going to get the z velocity in the negative direction because that's the radial direction. But because of the Coriolis effect, that's going to translate into deflection in the other two directions. So you're also going to start getting other velocities. We're going to assume that Vx and Vy are 0. as much as possible. And then we'll also say the centrifugal effects are approximately zero. So that's another assumption. And finally, we'll say the air drag is approximately zero. Even with this set of assumptions, the equations are going to be too complicated to solve, and we have to make various approximations. So, okay, let's write down the equation in the reference frame. So MR, I'm going to write this equation here. So MR double dot prime is going to be MR double dot plus 2m, that negative f core is just plus 2m omega cross r dot, which is velocity. And there's no centrifugal term, so we won't write the centrifugal term. So that's our only equation. And all this should be equal to the sum of all the external forces. So we can write our r double dot, which is going to be the external forces over m minus, because I've divided by m, 2 omega cross v. Now v is going to be 0, 0, negative gt, because initially there was no vx or vy. Omega is, according to this picture, omega has got only x and z components. The x component of omega is negative because it's in that direction, and the z component of omega is positive. So the x component is negative omega naught cosine lambda, because lambda is that angle. The y component is 0, and the z component is omega naught sine lambda. I'm calling the Earth's angular velocity magnitude omega naught, not because it doesn't change with time. Okay, so now we have to do the computation of omega cross v. Let's do that. Omega cross v is given by I hat, j hat, k hat. Omega is negative omega naught cosine lambda 0, omega naught sine lambda, and v is 0, 0, negative gt. So let's see what we get. So I get I hat times 0 minus 0. So that's I hat times 0. Negative j hat, don't forget that when you do the cross product, you have to do these sign assignments, plus, minus, plus, like so. So minus j hat, and what do we get here? Negative omega cosine lambda times negative t. So that's going to be omega naught gt cosine lambda, and then 0. And then k hat also will be 0. So there's only one term. Omega cross v is in the negative j hat direction. Well, the Earth is rotating from west to east in this direction. And so eastward deflection would be in that direction. Well, this is a westward deflection. It would seem it's a westward deflection, but it's actually an eastward deflection. I'll explain that to you. So that is the omega cross v. And now we'll write fx over m. Fx over m is just external force of gravity, and that's 0, 0, negative g. All right, we are ready now to write this equation. R double dot, which stands for x double dot, y double dot, and z double dot, is equal to fx over m, which is this, minus 2 times omega cross v, which is that. I'm using the ordered pair notation for vectors. It's easier to do in this case. So we have three equations, one for x, one for y, and one for z. Let us write them out. I get first equation is x double dot equals 0 minus 2 times 0. So x double dot is 0. If I integrate it, and I'll put these little integral symbols to show that I'm integrating, then I get x dot equals x dot naught, but the initial velocity is 0. So that is 0. And I integrate again. And that tells me that x equals the initial position x naught, but the initial position x naught and y naught are 0, and the initial height in the z direction is h. So we got to use that, those initial conditions, so that's 0. So this tells me that x at all time is 0. Not too exciting. The particle is not getting deflected to the south, in other words, because x denotes going south. Now that is, of course, an approximation, and it occurs because we have assumed the centrifugal effects are 0. If the centrifugal effects are taken into account, you have what's called Coriolis' second theorem, and you do have a southward deflection also. I'll leave you to either work it out or read up on that. Then y double dot. Y double dot, we have something. It's 2 because of the minus and the minus, you get a plus 2 omega naught gt cosine lambda. When I integrate that, I'm going to get t squared. So y dot equals some initial value y dot naught, but that's 0, plus omega naught gt squared cosine lambda. So non-trivial. There is going to be a deflection in the y direction. Integrate once more, and then I get y as a function of time equals y naught, which is 0 because it's pointing towards the origin initially, plus 1/3 omega naught gt cubed, because the integral of t squared is 1/3 t cubed, cosine lambda. So that's an important equation. Let's save that, call it equation 1. Now what about the z coordinate? That's the last equation to look at. Z coordinate is boring. It's just negative g. So when you integrate it the first time, so this is a standard vertical free fall z dot naught, which is 0 because the particles drop from rest, minus gt, and then I integrate again. I get z equals z as a function of time equals z naught minus 1/2 gt squared, but z naught is h initially. So we have our equation, z as a function of t equals h minus 1/2 gt squared. Okay, we want to find the total deflection. So let's solve for the time of flight, known as TOF, time of flight. Time of flight can be got by taking the value of z to be 0, because that tells you when the particle bites dust. So that tells me h equals 1/2 gt squared, or t equals the square root of 2h over g. Now we're going to use this and put it over there. So the deflection, y as a function of t, is going to be 1/3 omega naught g t cubed cosine lambda, and now we'll substitute for t cubed. So that's going to be 2/3 omega naught h square root of 2h over g. What I've done here is written t cubed as t squared times t. T I've written just like that, and t squared is 2h over g, which cancels the g there, and the 2 goes there, and the h is there, times cosine lambda. This is the famous eastward deflection of Coriolis. Because the value of y is positive, the particle gets deflected in that direction. And as I told you, the Earth is turning from west to east, so that's eastward deflection. Well, if the particle is getting deflected to the east when on its way down, it's also going to get deflected to the east on its way up. So if you're interested in succeeding in winning a war or something like that, you have to take into account this eastward deflection each time you fire a shot. In fact, the phenomenon that we have been studying was discovered by Coriolis, who was a French artillery officer. They found that in World War I, all the shells were missing their targets. And so they enlisted Coriolis's help to figure out what's happening. And Coriolis realized that the Earth is rotating under the, when you shoot a cannon, the Earth is rotating. And so when the cannonball lands, it's going somewhere else. So it never reaches the target unless you plan for it and adjust accordingly. So that is the eastward deflection, famous calculation of the French engineer Coriolis. Well, our final agenda item is to apply Newton's theory of orbits to see if the results agree with Coriolis's computation. So this is by far the neatest part of this video, I think, because Newton's theory is completely different. What happens in Newton's theory is that particles travel around the sun in an elliptical orbit. So let's remind ourselves of the essential facts of Newtonian theory. Here's an ellipse. So first things first, everything you learned in elementary physics is wrong. Particles do not travel in a parabolic trajectory when you throw a ball. When you throw a ball, the trajectory it describes is actually a portion of an ellipse. Okay, so here's your Earth's mass, and here's the ball that you're throwing. The Earth is represented by a point mass because the Earth can be thought of as a point by Gauss's law. So when you have a ball coming in to the Earth, it is falling along it's taking an elliptical orbit. Now, of course, the reason why you don't see this full ellipse is because the Earth is also pretty big. So before the particle has much of a chance to show its true elliptical nature, the particle lands on the ground. And this elliptical portion looks awful lot like the portion of a parabola because the heights are not much. But if you take a ball, say, to 300 or 400 miles from the Earth's surface, the description of that trajectory is not going to be a portion of the parabola, but rather a portion of the ellipse. So that's the North Pole, that's the South Pole of the Earth. This is the line joining the Earth and the ball. I'm going to call this angle theta. I'm going to call this angle theta prime. So we'll write this theta prime equals pi minus theta. That's pretty obvious. Now let's, so that's the description. Now let's actually put in the finite size of the Earth and see what happens in that frame. North, south, that's my omega naught. Okay, and my particle is coming along the section of an ellipse like that. Okay, so at any given time, let's start the particle at point P. Okay, and we'll start it at some initial height, h from the ground. All right. So when the particle does reach the Earth, let's make it a little 3D. When it reaches the Earth, it's going to be at that point. So this is Earth's radius r sub e, and so this angle that I have here, theta, is going to be the angle at any given time. So if I were to draw this like that, that's going to be my angle theta, described at any given time. Okay, and theta naught is going to be the initial angle corresponding to the point P. All right, so that's my setup. The initial R naught is RE plus H. Now the angular momentum is a conserved quantity in the Kepler problem. So the angular momentum in the z direction is mr squared theta dot. Well, let's try to compute the angular momentum at time 0. At time 0, the angular momentum, Lz naught, is going to be the mass times the velocity times the radius cosine lambda, because you have to project it along the latitude, okay, in the z component. So it's going to be m v r naught cosine lambda. But v is equal to r times theta dot. So that gives me mr naught squared theta dot cosine lambda. And theta dot is just omega. Omega naught, the angular speed of the Earth. So that's our computation of the initial angular momentum, and that angular momentum remains the same at all times. So we're going to use that fact. The other assumptions we're going to make here, also there are a bunch of assumptions. We're going to assume the reduced mass is pretty much the mass of the ball, because the reduced mass, remember, is the mass of the ball times the mass of the Earth divided by the mass of the Earth plus the mass of the ball. The mass of the ball is so small that I can ignore the denominator and write it as m times me over me. And when I cancel out the me's, I just get m. So when the reduced mass is always going to be in favor of the smaller mass. We'll also assume there's no air drag. It's in fact only if air drag is 0 that the torque is 0 and the angular momentum is conserved. So we need a planet without air to have this calculation. And finally, we also assume the angle theta always stays small. If theta is always small, we can make small angle approximations. And small angle approximations are going to save our skin here. So let us remember what r of theta is from the Kepler problem. You can look at some of the previous videos to find out what that is. The solution of the Kepler problem is it's going to be some value c plus epsilon cosine of theta prime, where that is theta prime, but we are working in the theta coordinate system, so that's going to be c over 1 plus epsilon cosine pi minus theta. Cosine of pi minus theta is negative cosine theta, so that's going to be c over 1 minus epsilon cosine theta. And the reason I know that is because cosine is negative in the second quadrant. All right, now we're going to use the small angle approximation. because theta is really small, I can write cosine theta as the first two terms of the Taylor approximation. The next term is going to be theta to the 4 over 4 factorial. We're going to ignore that. Okay, and we can use this to simplify some of the computations. All right, next, let's look at the angular momentum. The conservation of angular momentum gives me that the angular momentum at any time is equal to the initial angular momentum, LZ naught. The angular momentum at any given time is mr squared theta dot from that. And that's equal to LZ naught, which is mr naught squared from here, cosine lambda omega naught. So m's cancel out. That's Galileo's result. That mass cancels out. And so I have theta dot, which is basically d theta by dt. Well, that's going to be r naught over r, the whole thing squared, omega naught cosine lambda. We can immediately integrate this. So when I integrate this, I'm going to get the separate variables. So integral dt is equal to the integral of d theta divided by r naught over r squared omega naught cosine lambda. So this goes from 0 to time of flight capital T, and this goes from 0 to theta naught. Theta naught is the angle when it hits the ground. Okay, so that is the state of affairs. Now we have to solve this integral. Well, omega naught and cosine lambda are constants, so I'll pull them upstairs. So I'm going to get total time t times omega naught times cosine lambda. All that's going to be the integral from 0 to theta naught d theta over r naught, which is basically r at 0, over r at some random angle theta, the whole thing squared. So we have to solve that. We have this orbit equation, so I can use that to put theta equals 0 and see what I get. So I get c over 1 minus epsilon, because that's what I get when theta is 0. What about r as a function of theta? Well, that's just c over 1 minus epsilon cosine theta, but I have to make the approximations, so let me do that. If I don't make the approximations, I get this horrible elliptic integral, and we don't want to be there. So I'll make the approximations. So I get c over 1 minus epsilon. Cosine theta is 1 minus theta squared over 2 factorial, which is just 2. So this is c over 1 minus epsilon. I'm going to take 1 minus epsilon outside because I already have that over there. And then I'll write everything else doctored up. Since 1 minus epsilon is common and I have theta squared over 2, that becomes epsilon over 1 minus epsilon theta squared over 2 plus 1. But let's make sure nothing illegal has happened. When I take 1 minus epsilon, I get 1 minus epsilon, and then these two will just give me epsilon theta squared over 2. So that's right there. So it's exactly what it needs to be. Okay, so we have this r of theta, but this part is just r naught. So we can write r of theta is just r of 0. So in this fabulous manner, I've got rid of the factor c, the thing in the numerator. And now I just have 1 plus epsilon over 1 minus epsilon theta squared over 2. But epsilon is the eccentricity of the orbit. All right. Now let's see what we can do. with this. More approximations are going to be made. We're going to keep milking this small theta for all it's worth. So this tells me that r of theta over r naught, actually I need r naught over r of theta. So r naught over r of theta is going to be 1 plus epsilon over 1 minus epsilon theta squared over 2. Now I have to square this because that's what I have. So r of 0 over r of theta, the whole thing squared. Well, that's going to be this squared. But I'm going to get terms like theta to the power 4. We're going to ignore that. So I'll just keep the first term. When you do a plus b squared, you just get a squared plus 2ab. I'll just keep the 2ab part. When the 2 will cancel with this 2. So that just gives me 1 plus epsilon over 1 minus epsilon theta squared. All right. So now we have to determine epsilon because we don't know what that is. We can use the fact that the particle lands at angle theta naught. So the landing, let's look at the landing. So r of theta naught, which is going to be radius of the Earth, and that is just c over 1 minus epsilon cosine theta naught. From this, we can find epsilon. So let's see if we can do something better. Actually, we can use small angle here also, because cosine theta naught is also small, because theta is small, theta naught is small. I'll use the exact same tricks as I have here. So I'll write Re equals c over 1 minus epsilon. I'm just copying this from here. 1 plus epsilon over 1 minus epsilon theta naught squared over 2. The only difference is I put theta naught squared. And that c over 1 minus epsilon is just r at 0. So that's 1 plus epsilon over 1 minus epsilon theta naught squared over 2. Okay, what is r of 0 though? R of 0 is the radius of the orbit plus the height h. So we're going to use that next. Let's use this. So I'm going to get, I'll write this term on the left side and pull r sub b on the denominator and write r sub b plus h for that one. So let's see. Well, this is just 1 plus h over r sub b. And I'm going to call this factor h over r sub b. I'm going to call it by the factor eta. So I have 1 plus stuff equals 1 plus eta, which means I can cancel the 1s on both sides, and I have epsilon over 1 minus epsilon theta naught squared over 2 equals eta. So we are almost there. Epsilon over 1 minus epsilon is going to be eta times 2 over theta naught squared. All right, so now I have to put it back there. So I get r of 0 over r of theta, the whole thing squared, is 1 plus, instead of epsilon over 1 minus epsilon, I'll put eta times, there's a 2, so I'll write it as 2 eta times theta squared over theta naught squared. So beautiful symmetry about this equation. Now I'm going to put it back in this integral, and hopefully I can work it out. Okay, again, my hope is not to do much work at all. So t omega naught cosine lambda is going to be the integral from 0 to theta naught d theta over this quantity Well, this can be written as integral 0 to theta naught. At this point, you can actually be honest and you can make a substitution, tan substitution and things like that. But I don't want to mess with the inverse tangent function and then look up the asymptotics of that. So rather than do all that, I'll cut all that in the initial stages itself by doing an approximation here itself. This can be written as 2 eta theta squared over theta naught squared to the power -1 d theta. And now I can use the binomial theorem approximation right here. So the binomial theorem approximation, recall, says that 1 plus x to the power n is approximately 1 plus nx, whatever n is, as long as absolute value of x is much less than 1. That is abundantly satisfied in this equation, because not only is eta much less than 1, since h is much smaller than the radius of the Earth, but theta is also really small. So it's a double whammy small quantity. So it's abundantly satisfied. And so I get n is -1 in this case. So I'm going to get t omega naught cosine lambda is equal to, or put an approximate sign there, the integral from 0 to theta naught 1 minus 2 eta theta squared over theta naught squared d theta. Now this should already make you pretty excited because you see the 2/3 factor coming from this computation. So the integral of 1 is just theta, and so the limits are going to be theta naught minus 2/3 eta. This is going to be theta cubed over theta naught squared. So when you put the limit of theta naught, I get theta naught cubed over theta naught squared, which is just theta naught. So that's just theta naught times 1 minus 2/3 eta. All right, so we can now solve for theta naught. So theta naught is approximately equal to t omega naught cosine lambda over 1 minus 2/3 eta. Now I can use the binomial theorem approximation again, and this becomes 1 minus something to the power -1, so it becomes 1 plus that. So it's t omega naught cosine lambda times 1 plus 2/3 eta. Now, in that time t, how much has the particle traveled along the Earth's surface? Think of the shadow of the particle. That so the shadow has traveled an angle theta naught. So we'll call that shadow travel delta y spatial. Well, that's just going to be the Earth's radius times theta naught. But meanwhile, the Earth as itself turned through a distance. So delta y Earth is going to be re cosine lambda, because the radius of the Earth at latitude lambda is re cosine lambda, and the Earth has turned by that distance, delta theta Earth. Well, delta theta Earth is just omega naught times the time of flight. So this is just re cosine lambda times omega naught times t. Why are we looking at both these deflections? Because you have to take the difference of them to get the true deflection. So the true deflection delta y is going to be delta y in space minus delta y of the Earth itself. Remember, this is a reference frame fixed to the stars. So we have to look at how much things have moved in space and how much the Earth has moved. So I get delta y of space is just that. So re theta naught minus re omega naught t cosine lambda. Meanwhile, theta naught is all of that. So let's put that in. So that re t omega naught cosine lambda plus 2/3 eta re omega naught t cosine lambda minus re omega naught t cosine lambda. beautiful, almost miraculous that you have this cancellation. So in a sense, the spatial um, displacement is exactly taken care of by the first order level calculation, and then the higher level calculation gives you the Coriolis deflection. So this is just 2/3 eta is h over re, and then I have re, so the two re's cancel. Omega naught, the time of deflection is square root of 2h over g. That's the usual time of deflection of a particle, time taken for a particle to fall at constant speed, cosine lambda. And if you notice, this exactly matches with the Coriolis calculation. It's amazing. To me, this is really amazing. That Newtonian methods and Coriolis. And look at how many approximations we made here, like tons of approximations to get this result.